approach for handling this is something called a cross-validation. And this is something some of you already mentioned in the chat room. And in this case here, what I do here is, so in this case here, I'm going to do split multiple times. So which means I'm not going to fix, I'm not going to have a fixed set of data only for training, another set only for validation, another set only for testing. Instead, I'm going to divide my data, entire data, into a few folds, k equal sized folds. So in this illustration here, I'm dividing data set into 4 equal sized folds randomly. So this first fold, second fold, third fold, and fourth fold. And then what I'm going to do here is this. I'm going to do in this procedure of cross-validation. I'm going to cycle through each one of the fold here and treat each one of the fold as validation data sets, right? So I'm going to start with this ones here, start with the first ones here, and the first row here. In that case, I'm going to use this data sets here from first 3 folds for training my models. When I say training here, that you can literally, narrowly speaking, just learn the parameters of one particular models, right? Maybe I'm going to use now learn the parameters of a linear models, or learning the parameters of a polynomial functions of that. So that's for the learning parameters of the model. And then what you can learn that for multiple models, and then you're going to do validations here. So among all the models, you're going to see which one, what the performance of that models. You can see the performance of that models on this, on the remaining fold of that, right? So, and then what are you going to do here? You're going to cycle through each one of them here, and you go through the second row here, and you use data from fold 1, 2, and 4 as your training data sets, and then you evaluate the performance on the third fold and then cycle through them. So the benefit of this type of cross-validation is this, right? Because I'm not using fixed sets of validation data. I train my models by cycle through them. And also because I evaluate them on this validation set multiple times here. You can see multiple times here. So I can afford to use a smaller number of data for validation. So this is not the case in the previous cases here. When I use data for validations here, I need to make sure that I reserve sufficient large number of data for validation, because otherwise my evaluation may not be reliable. There might be too much fluctuation if your validation data set size is small. However, when I do cross-validation here, I can do this multiple times. Altogether, they have multiple kind of enough size for evaluating the performance of data set. However, it comes with disadvantage. The disadvantage of this cross-validation is this. You have to train your models for each row here. Every time the models, learn the models will be different because you are using different set of training data set to learn your model. So they will be different. So however, we care about it is not try to identify the best models, but instead we try to identify the best methodology. Well, is this linear model better than quadratic functions? Is polynomial, seventh order polynomial better than the second order polynomial? Or is neural networks better than SVM? Or based on decision tree? And that's for the model selection purpose. And that's very useful. And this is something called a cross-validation purpose of that. So in the cross-validation here, of course, you have to choose something K here. K determines how many folds you need to split the data sets here. And then that comes with many degrees of choices here. Some people choose differently here. There is pros and cons associated with the choice of the K here. In the extreme case, the most commonly used fold is 5-fold or 10-fold cross-validation. For instance, in the 10-fold cross-validation, essentially you split data set into 10 folds, and every time you use 90% of the data for training, and the remaining 10% for validation purpose of that. And you can also do another extreme called leave one out cross-validation. So in that case, you use over 99% of the data, use all data but one for training, and you're going to evaluate performance of that model only on the one samples. So clearly, that's a lot of bias in evaluate, not a lot of variance in evaluating the performance here. But the idea is that in the end, you average performance across different folds, and you get a average performance of your models. in that case, many cases, it turns out to be a reasonable kind of evaluation, assessment of your competitions, right? For instance, and in the future, you might want to participate in these Kaggle competitions. So the Kaggle competition, what commonly users do is this: they split the data sets into this exactly three sets here. And usually what they're going to do is release this training data set to you, and then you can download this data sets, and you can train your models on the training data sets. And then they have something called a leaderboard associated with all these Kaggle competitions. And leaderboard usually are active, real time, and then you can submit your models. You can see the performance of your models right away. And those models are evaluated on this so-called validation data sets. And you can see feedback right away. So for instance, and that's very common for the Kaggle competitions here. And each row here is one team, one submissions, and you see the scores here, right? The scores here is the performance of your models on the underlying validation data set. So this validation set is not visible to the participant. If you ever participate in the Kaggle competition, you don't see the validation data sets, right? You only submit your models, and your models are evaluated by the hidden validation data set by the organizer. Organizer have this validation that they can assess your model, but you don't see them, right? But you will be able to see the scores of them. You can submit as many models as you like, and you can say many different times here, and so on. So that's where you can see, for instance, this number shows you how many submissions, and this team have throughout these challenges here. It has submitted 40 models. And then this is the performance of the best models. And that's what it says here, right? And essentially, this is doing a model selection process. And you submit more models. In the end, you pick up the best models here. So that was done here. So however, and for many of you ever participated in Kaggle challenge, you know that the result in the end, what's the ranking of the different teams, which team win the competition, is not based on the leaderboard rankings. So this is called a leaderboard rankings. And it's not based on that. It might be very common to see that. So now this team called a Brick Mover now ranked top 1 along in the leaderboard. But it's not surprising you will see that in the end, the final rankings assessed by the organizer here, and he's not the number 1. And maybe somebody down here turns out the number 1 ranking teams. So why is that? Because the final ranking is going to be based on the test data sets and held by the organizers here. And only organizers know the test data sets here. And then, all the participants here doesn't know the test data set. So they're only going to evaluate your models on the test data only once. So only evaluate only once here. So unlike the validation data set, you can evaluate your models and then you can see the performance multiple times. But test data only be able to see the result once. And that gives you a better sense to estimate the real world performance of that. And that's, in fact, that's also the final rankings. All the Kaggle competition is based on those test data sets here. So sometimes the reason here is this. So this performance here, you may ask me here, I think a related question here, you have, this team and Brick Mover ranked number 1, how come this team here in the end ranked maybe in 10 in the final rankings? The reason might be this, right? And this team here submitted way too many entries here. It just might be lucky that there's one model by chance performed better on this kind of evaluation data sets. Does not mean that this model is a better model than the other models of that. So, the performer, the participant can't be fooled by these type of rankings here. So for experienced Kaggle competitions here, they actually will control the number of submissions they want to submit here. They do not want to submit too many entries, because once you submit way too many entries here, and those numbers here is not informative anymore. So they have to be so now for very experienced ones here, you look at the leaderboard here, and then you want to say, who is going to be final winner of this challenge here? I'm going to look at ones here and top 5, maybe top 10, and look at the ones here. I'm going to find the ones here who has less number of entries. And more likely, and those models here has less overfitting on those validation data sets, and turned out can be generalized better on the test performance.